Okay then, let's look at how to fit a growth mixture model in M+. Here we have a quadratic growth curve model that we used in a previous example where we have child internalizing behaviors from age 10 to age 16. And we have here our intercept, linear slope, quadratic slope, and then we have our specification of time. We have all of our internalizing variables, 10 through 16 here, and then our specification of time, 0 through 6, and our plots. Now we can just directly turn this into a mixture model. First thing we're going to do is we're going to go in here to the variables command, and we're going to type in classes equals C, and you can name this anything you want. This is just naming our class variable, but I'm just going to name it C, and then parentheses, and then how many classes you want, and we're going to start out with a single class. Then we have to change our analysis. So we're going to go to the analysis command, the type equals mixture. These are mixture models. And then we're going to go to starts. Now, if you remember back from the lecture, if you look at those slides, you'll know that these starts are the number of random starts used in order to find the global maxima. That's the optimal solution. And I'm just going to start out with 200 and then 20 here. Often this will be about 10% of the other. If you start running into problems, then you might change these numbers. 200 is probably pretty low, but for the sake of demonstration, I'm just going to use that so we don't have to watch these models run for too long. Now I'm going to put in processors. Most computers now have more than one processor, and you can specify the number of computer processors that M+ will use to calculate all these starts and find the maxima there with each one of those. I'm going to put, well, let's do 11 processors. I have 12 processors, but let's just save one to do other things. So I'm going to put in 11 processors. Most likely you have about 4 processors on your computer, and you can specify all 4 of those. Next we're going to go here to the model, and we need to specify our overall model. Now you can actually specify models specifically for each one of the classes and do some constraints in there and have each class model be a little bit different. We're not going to go into that here, but we're just going to say here then that this is our overall model, and the parameters that it's going to allow to vary across are going to be of what's most interest here, the means and variances of these latent variables. We're also going to add an output. We want to get our Tech 11 because our Tech 11 is going to give us our model comparison. So for the one class, it's not going to give us a model comparison because it's not comparing to, well, a 0 class model. The model comparison is always to a model with one fewer classes. So here we have just the one class. I'm going to put Tech 11 here anyway because we're just going to edit this for 2, 3, and 4 classes. So I'm going to put that in there. Well, we'll save this now, and we will fit the model. You can see here my 12 processors went very quickly. And of course it says that there's a warning, the Tech 11 not available for type equals mixture with only one class. We knew that. We're going to go down, and the first thing we're going to do is, because as you remember, we need to find out which fits the data better. Here we have our AIC, BIC, and our SABIC right here. I have this Excel file here that's going to calculate all of those and more for me. And so what I'm going to do is I'm just going to take this likelihood value, I'm going to plug it in here, I'm going to take the number of free parameters, which is 16, plug that in here, the N I'm going to put in here. Let's go up here and make sure that my N is right, 681. And that's calculated my BIC, SABIC, AIC. I always do like to look here and make sure that I do have it correct. So let's say my BIC is 1238, 1238.23. It is the same. And here you can look and see this is our growth model. And this is identical to a model that we didn't specify mixture and we just did the one class. Essentially, the regular growth curve is a one class solution. Alright, so we have that information and we're going to go on. So I'm just going to close the output, and in order to get a two class solution, all I do is put a 2 in there. Save that, run it. All the different threads are going to run. And we're going to look down. Now here we have a message that's important to look at. The best likelihood value has been replicated. That means it's very likely that you did obtain the global maxima. However, it's still going to invite us to rerun with at least twice the random starts to check to make sure that the best likelihood was in fact obtained. We're not going to do that here, but that really isn't a bad idea. Say use 400 starts, and just to make sure that you do get the exact same solution, to make sure that this number doesn't change on you. If this number here is changing on you, your log likelihood, that means your parameters are also changing. So again, I'm going to put this in here. Our number of free parameters is 20, and the number of the sample size is the same. Now what we're going to start getting here is some information on these latent classes. Before it was just 100%, so there's nothing very interesting to look at here. But here we have class number 1 that represents about 62 people in the sample. Why only 62 people? Why 62.68, not 62 or 63 exactly? Well, that's because this is an estimate, and the putting people into classes is probabilistic. It's not definite. It doesn't absolutely classify individuals. And so about 9% of the sample is in that first class, and 91% of the sample is in that second class. Now we have our entropy. And entropy is telling us whether or not we're actually classifying individuals well, whether or not that probabilistic classification indicates that people have a high likelihood of being maybe in any class, and so no classes are really very distinct. So I'm going to actually copy this, and I'm going to put it over here because I like to keep track of my entropy as well. So I'm going to put my entropy right in there. These are some other ways to look at the classification. This is most likely latent class, so this is absolutely. So if they were to be absolutely put into one class or another, then this is what the counts would be. And you can see that that's a little bit different, not too different from the other. These are some other things. We're not going to go over them in this, but essentially it's about misclassification and how likely it would be that somebody might have been misclassified. And now we have our results. So this is for first one, latent class 1. Here's our means for the intercept, linear slope, and quadratic. You can see that it really is just a straight line essentially, because the linear and quadratic slope are not significant. However, there is variance around that linear slope that you could predict. Now we go down to class 2. Here's the estimates for class 2. And you can see quite a different story here, where we have significant linear slope, significant quadratic slope, and variances in the linear slope, but no variance in the quadratic slope. Let's take a look at those. So I clicked on my diagram. This is what I get because I did the plot. Estimated means, you can see it's really nice to give us these two. So as you remember, this one, class 1, the linear and the quadratic slope weren't actually significant. However, using the scale, it looks like there's quite a bend there, but they weren't. But the linear and quadratic slope weren't significantly different from 0. Now you have, here's the class 2, the blue one. So you can see these follow a bit different pattern. All right, close that. And now we're going to go down and look at our log likelihood tests. Here's the VLMR likelihood test, and this is just the LMR. They have a bit of a difference to them. I would probably go with the VLMR, but they're often going to be almost exactly the same. So I'm going to say here that the difference test was less than 0.001. And what this means is that the two-class solution fits the data significantly better than the one-class solution. So this is some evidence that the two-class solution is in fact better than the one-class solution. What I'm also going to do is I'm going to record the best start value. And that's back up here, right here. This was our best start value. And if we put that in there, that is going to, I'm going to record that here so that I can recreate this analysis. There's an OPT seed that you can look up, OPT seed, and you can specify it as this, and you can do 0 starts, and it will replicate this very solution. Okay, so that is our two-class solution, and you can see here that the BIC does drop, meaning better model fit. Really, all of these drop. And by filling in this here, we're also creating some graphs. So you can see here that, yes, the model does fit significantly better, or I shouldn't say significantly better, but the model fits better. And these are all dropping to the bottom because these other ones here aren't filled in. So now let's do our three-class solution. We'll go ahead and fit that. You might start to hear some noise from my computer when I do this because it's working really hard and the fan gets going. So let's go ahead and record everything that we want to. So this was our best start seed. So we'll put that here, again, so we can replicate this if we want to in the future. Here it says the log likelihood has been replicated. That's good. And then our invitation to rerun it again. Here's our log likelihood value. Copy, put that in there. Number of free parameters is 24. And our N is 681. You can see that this, so here's our class memberships, and you can see that the first class now is the biggest class. These can move around quite a bit, and there's a trick to be able to get them to stay by specifying certain things within your model command. Again, we're not going to go into that here, but that's something that you can look into to do. So here we have our largest class, 87%, 89%. Then we have a smaller class that's only 4% of the sample, represents 24 individuals. And then we have this 9% class, which represents 58 individuals. Now this is a fairly small class, and we might wonder, is this just the tail end or a more extreme version of class 1 or 3? Well, let's take a look at it. Let's look at our plot and see what this class looks like. So I'm just going to my plot, estimated means, and this class 2, those 25 people, they look like they follow a very different trajectory than these other classes. These other classes, they're pretty much what we had identified for before. They look the same, but now we have this one class. Maybe they're a clinical class and which clinical levels of internalizing problems, but they start out about average. They even drop a little bit, but then all of a sudden something happens. This is about age 13 that their internalizing problems just skyrocket. So this really does look like a very different class, and I probably would consider keeping that class just based on the conceptual criteria, but we also want to look at the fit to see if it fits the data better. And as you can see, as we've now populated these, our SABIC and our AIC have decreased, and so by those standards, yes, the model is fitting better. And here we have the BIC, and the model is also fitting better, indicated by the decrease. Now I have entropy here, so let's find our entropy value, and we can put that in right here, entropy 0.923. The entropy is actually a little higher, which is good. The closer to 1 that entropy is, the more indicative that we are actually classifying people pretty well. Let's go ahead, I won't look through those estimates, but let's go ahead and go down to our log likelihood tests. As you can see here, the p-value is significant. So the difference test is less than 0.001, indicating that the 3-class solution fits better than the 2-class solution. So there's a lot of indicators here that the 3-class solution fits a lot better than the 2-class solution. Let's go ahead and now run our 4-class solution and see what that looks like. Save it, run. Okay, here was our 4-class solution. We'll get the best start here. We'll get our log likelihood, our number of free parameters being 28, and our sample size being 681. And here we've identified a class that looks to be pretty small, only 10 people in that particular class. The other classes seem to be pretty much the same in terms of their size. So let's go ahead and take a look at this new class, and this is our class number 1 in this particular model, estimated means. So class 1 here is this red one. Now the question is it substantially different from our other classes? Well, it seems to be following this exact same pattern that class 2 was. In fact, our class 2 was a little bit smaller, almost by the degree, not quite, that this is. And so we might have just broken out our previous class into 2 classes. So it's pretty much following that exact same trajectory, only much higher. Let's take a look and see how our test between the 3rd and the 4th class went. Well, it's not significant. So we would conclude that from this, the 4-class solution does not fit the data any better than the 5-class solution. So if this is greater than 0.05. Let's go up and look at our entropy, get that. Entropy is pretty much the same. And now if we look at our fit statistics here, we see that the SABIC actually seems to increase a little bit. And so does the AIC. Here's the AIC, it just barely increases. And the BIC also increases. So based on this, based on the fact that it doesn't look like the 4-class solution gives us a conceptually different class, based on the fact that the SABIC, AIC, and the BIC actually indicate a worse model fit, we'd probably conclude from this that the 3-class solution is the optimal solution. And we'd stop there. Let's go ahead and fit a 5-class solution just to extend it out a little bit. Go ahead and run that. This will take a little while. You'll see, notice this will count to 200. And then it will perform some other operations. And my computer, you can hear, is working hard at this. And what you see here is what sometimes will happen when we push our mixture models perhaps a bit too far, where you have the covariance matrix not being positive definite for any of the classes, and so it's saying check things. Now, it may be that there is something there. I don't want to indicate that you should absolutely stop if you have some errors, but this is pretty typical when we try and overfit a model, that you get non-positive definite matrices. And so if I really wanted to get this model 5 to fit, I would really have to go in and start tinkering with each of the classes individually to see what's going on there. But I'm just going to leave it at that, because it starts fitting worse after 3 classes. Really, by all indications, the 3-class solution is the one I'm going to accept as the final solution here. So that's how you fit a growth mixture model in M+.